Hi there, we're going to look at reductions and oxidations of organic compounds. If you remember the term Leo, the line GER, GER, gaining electron is a reduction. So that's in green, it's a reduction. I kind of try to color code that. So when you do a reduction in organic compounds, mostly hydrogen palladium catalysis, and it will add hydrogens. It's also called the syn addition, same side. That's what I'm trying to show you. Now, so where to add these pi bonds? It could be double bonds or triple bonds. For clarity, we'll just take a double bond, 2-butene, and we will get just an alkane, butane, as a result. So we do have two other hydrogens. Originally, we had it in the compound, so they should be actually solid and dash. So I'm marking here. The palladium catalyzed hydrogen came from the bottom, that's why it's dashed. And we can kind of think the metal catalysis happens, the metal is a surface, the metal is palladium platinum, and the hydrogen is absorbed onto that surface. So this pi bond docks onto that and react and takes from the bottom side two hydrogens of the double bond. That's what I'm trying to show you. Right now, also in red, Leo, losing electron is oxidation. So we can actually do an oxidation. How do you do that? If you remember, HOH can be added across the double bond. That's actually electrophilic addition, but it will oxidize though, right? Further down. So in this case, we are adding an oxygen into the double bond. I am neglecting the oxidation numbers for this situation. You know, this secondary alcohol can go further to the ketone. That's where the oxidation number will change. We'll focus on that later. But look at this one. Going this direction is oxidation. Losing electron is oxidation, right? So that's what I was trying to show you. And now we'll look at, again, in the sense of oxidation numbers. Let's look at here. So if you look at CH4 and fully oxidized version is CO2. There's nothing beyond CO2 to be oxidized, right? So therefore, CH4, carbon, we are looking for the oxidation number. 4 hydrogens is 4. That means carbon is -4 for the CH4 methane. But for the CO2, carbon we are looking for 2 times oxygen -2. That means C is +4. So when the carbon is +4, it's fully oxidized in the oxidation number. When the carbon is fully hydrogenated, it's -4. Now, in this compound, when you have 2 hydrogens, the oxidation number is -2. When you have 4 hydrogens, you had -4. Here, you have 1 oxygen and 1 hydrogen, so that would be actually 0 oxidation number. So you can try to calculate that too. And in this one, double bond O would be a +2 oxidation number, because oxygen gives you -2, then the carbon should be +2, right? So the neighboring carbons we neglect. So that's a good way if you have a larger organic compound. This one, there is 3 oxygen bonds. You can simply think carbon has a +3, right? And you had CO2, 4 bonds of oxygen, that would be carbon +4. That's what we've shown, right? So there's another way to think. Look at the 2 hydrogens give you 2 electrons to the center carbon. It would be -2. Here, 1 electron given, 1 electron taken, and therefore the center carbon should be 0 oxidation number. Here, you would have 2 electrons taken away to the oxygen, so therefore center carbon would be +2. Now here, there's 3 oxygen bonds, so 3 electrons taken away, so the carbon should feel +3. That's another way to look at it, right? Now, one advice, in organic compounds, it's better not to go to full calculation. It is a comparison between A and B oxidation reduction. That's how you want to do it, right? Because you don't want to count the oxidation number for like cholesterol or benzene ring, something like that. Now, so another thing to pay attention, the right side of this material going to the left is process is oxidation in my writing here. So oxidation by whom? By MnO4 minus, Cr2O7 2 minus, it could be CrO4 2 minus, could be ozone O3, could be any of these reagents will oxidize the reducing agent on your right. It could be any of those +3, +2, 0, -2, -4, right? You mostly end up with the CO2. Now going the other way from left to the right, starting organic compound is oxidizing agent. It will be reduced by one of these reagents. What is that? Lithium aluminum hydride or sodium borohydride or hydrogen catalyzed. So lithium aluminum hydride is a stronger reagent, and you can see the oxidizing agent. The reagents are a lot of oxygens in the oxidation process, and the reduction process you have a lot of hydrogens. So those are the things should make more sense. And so you think about the Leo, the line, GR, and then think about the oxidation reduction number line, and think about the reagents and whom get oxidized and whom get reduced, and who is the secret agent Ra, who is the secret agent oxidizing agent, right? Because secret means oxidizing agent getting reduced by lithium aluminum hydride, or oxidizing agent getting reduced by sodium borohydride. That's the idea. Now, so next thing to know about the alcohols, if I get this alcohol and it's a propanol, right? And one propanol. In this case, you have two hydrogens sticking out from the carbon, first carbon, OH attached. And if you oxidize, you will end up with propionic acid, this one, the carboxylic acid. Now, we can see what's the reagent. So we know oxidation took place, so then the reducing agent would be the alcohol, right? And it's been oxidized by the MnO4 minus or Cr2O7. So Cr2O7 is actually an orange color reagent, very nice. And you can see this free oxygens come and take these two hydrogens, kind of, you can think that way, right? Now what happens, you put another oxygen and making a carboxylic acid. When you do that, actually Cr2O7 orange will go to green. Another thing to pay attention, look at the R group, any alkyl group. When you have one R, it's one ROH, or it's primary alcohol. So the primary alcohol will give you carboxylic acid after the oxidation, right? Now another thing to pay attention, if you distill putting these reagents together, you will end up with the middle compound, and then if you reflux, you will go all the way to the carboxylic acid. So that's the fundamental difference. You also, if you learned about PCC, PCC will stop in the middle. What is that? That's an aldehyde. So the aldehyde have a double bond O and a hydrogen. So the aldehyde is actually in the middle between alcohol and the carboxylic acid. So reflux is many distills. Simply it's a minor difference in the apparatus, right? Okay. Now second one, you have an alcohol and it goes to by oxidation, it will create a ketone. So this one has, look at this ketone, double bond O, and two R groups attached, right? And we label ketone, and then two R groups attached, double bond O, ketone. And look at, this is an R group, this is an R group. Two R groups, let's say two ROH, or you call it secondary alcohol. And secondary alcohol oxidation will give you ketone. So no matter what reagent actually you are using, you can use stronger reagents, you can use mild reagents, right? Now, third one is much simpler. So you have OH attached to three R groups, then I should write 3 ROH, or we call it tertiary ROH, and no reaction. Now you can think, why is that? If you note, this is tertiary alcohols have no reaction. The reason is they are missing these oxygens. Look at here, this secondary have one hydrogen and primary has two hydrogens to lose. That's why.